Decoding the Kaaba, a mathematical exploration. This analysis explores the compelling geometric and proportional relationships surrounding the Kaaba. Moving beyond formal academic research, this exploration uses available tools like Google Maps and coordinate projection to analyze the positions. Kaaba focuses on observing patterns, not on proving a scientific thesis. By plotting the Earth's latitude and longitude on a 2D grid, we can analyze the Kaaba's coordinates 21.4 to 3 degrees north, 39.8 to 6 degrees east. The distances from this point to major global lines, like the anti-meridian and the north and south poles, yield ratios that closely approximate key Fibonacci ratios like 5 to 8 and a near-perfect 13 to 8. Intriguingly, the sequence of numbers 5, 8, and 13, when mapped directionally, creates a counter-clockwise spiral, mirroring the very direction of the Tawaf, the ritual of circulating the Kaaba. The analysis also extends to the immediate vicinity. The geometric relationship between the Kaaba and the Maqam Ibrahin, the station of Abraham, appears to mirror the larger relationship between the Kaaba and the Earth's coordinate center, sharing a specific angle. Furthermore, the boundaries of the Haram, the sacred land surrounding Mecca, display their own proportional consistency. The distances from the Kaaba to several Haram border in all four cardinal directions form simple ratios of 2 to 1 and 3 to 2. Disclaimer: AI assists in material discovery, text composition, wording refinement, and translation. Kaaba ratio to the Earth's poles, inspired by online video on the same theme. Kaaba and golden ratio, calculate with different calculation and perspective. The Earth's spherical coordinates latitude and longitude were projected onto a 2D Cartesian plane, and the resulting coordinate points were plotted in Inkscape to ensure scale consistency. Furthermore, the satellite imagery from Google Maps was utilized as a visual reference to confirm the positions of the Kaaba and Maqam Ibrahim. Fibonacci is the Fibonacci sequence, one of the most beautiful, not the only one, mathematical patterns found in nature. Yes, the Fibonacci sequence is widely considered one of the most beautiful mathematical patterns found in nature. Its beauty stems from its elegant simplicity and its surprising prevalence in the natural world. The sequence is defined by a straightforward recursive rule. Starting with 0 and 1, each subsequent number is the sum of the two preceding ones, that is 0, 1, 1, 2, 3, 5, 8, etc. The way this simple pattern manifests in the growth and structure of living organisms, from the smallest plants to the largest galaxies, is what makes it so captivating and beautiful to mathematicians and scientists alike. The sequence was introduced to the Western world by the Italian mathematician Leonardo of Pisa, known as Fibonacci, in his 1202 book, Liber Abaci. The frequent appearance of the Fibonacci sequence in nature is not just a coincidence. It's a result of natural processes seeking the most efficient and optimized patterns for growth. These patterns, known as phylotaxis, allow for maximum space utilization and exposure to resources like sunlight. The mathematical regularity provides a framework for biological forms to develop in an organized, balanced, and harmonious way. This underlying order gives rise to the visual appeal we see in many natural objects. The beauty of the Fibonacci sequence is also tied to its relationship with the golden ratio A. As you move further along the sequence, for example, 8/5 equals 1.6, 13/8 equals 1.6 to 5, 21/13 equals 1.615, the ratio of any number to its predecessor gets progressively closer to approximately 1.618, the golden ratio. This ratio, often called the divine proportion, has been used by artists and architects for centuries because it's considered to be inherently pleasing to the human eye. The fact that this aesthetically pleasing ratio emerges from the simple Fibonacci sequence and is so frequently observed in nature's designs adds to the overall sense of wonder and beauty associated with this remarkable pattern. To be honest, does not all of nature follow the Fibonacci sequence? You're absolutely right, not all of nature follows the Fibonacci sequence. While it's a fascinating and common pattern, it's just one of many mathematical principles at play in the natural world. Other mathematical patterns in nature. Nature is incredibly diverse, and one can find a wide variety of mathematical and geometric patterns that aren't based on the Fibonacci sequence. These patterns often arise from the most efficient way for things to grow, pack together, or disperse. For instance, hexagonal patterns, The hexagon is one of the most efficient shapes for tiling a flat surface without any gaps. This is why it is seen so often in nature, from the cells of a beehive to the basalt columns of places like Giant's Causeway in Northern Ireland. Fractals. These are complex, self-repeating patterns where a small part of the structure looks like the whole. You can see them in snowflakes, coastlines, Romanesco broccoli, and even the branching of trees and lightning bolts. Fractals demonstrate a different kind of mathematical order, based on iteration and scaling, not addition. Symmetry. This is one of the most fundamental principles in nature. From the bilateral symmetry of a human body to the radial symmetry of a starfish or a flower, it's everywhere. Symmetry often relates to an organism's lifestyle and how it interacts with its environment. Analyzing the position of the Kaaba. The geometric diagram used in this analysis is not drawn directly on the surface of a globe. Instead, it is a projection of the Earth's spherical coordinates latitude and longitude onto a two-dimensional Cartesian plane. This means that each point, such as the Kaaba, the poles, and the anti-meridian, is originally defined on the curved surface of the Earth, but is represented in the diagram using XY coordinates on a flat map. This type of projection is necessary because spherical geometry cannot be displayed on a flat page without distortion. When latitude and longitude are converted into Cartesian coordinates, certain geometric properties, such as distances, areas, or angles, may become stretched or compressed depending on the chosen projection method. Therefore, the diagram preserves the relative placement of points based on their real Earth coordinates, but it should be understood as a flattened representation of a spherical model rather than an exact reproduction of Earth geometry. In this context, the diagram functions as a conceptual and geometric tool, allowing relationships between points to be visualized and analyzed within a flat coordinate system, while still being grounded in the true positions of those points on the spherical Earth. We can place Google Maps into a 2D Cartesian coordinate system, and in fact Google Maps already is a 2D Cartesian system, created through a projection called Web Mercator. Kaaba into 2D Cartesian coordinate system. The diagram places the Kaaba within a coordinate-like layout based on major Earth reference lines, the North Pole at the top, the South Pole at the bottom, the equator in the center, and the prime meridian and anti-meridian on the left and right sides. The vertical lines longitude are colored green, and the horizontal lines latitude are colored red. The white color represents the Kaaba's position. At the center of the diagram is point C, which represents the coordinate center. Point K marks the location of the Kaaba at 21.4 to 3 degrees north and 39.8 to 6 degrees east 7 GH x CRFG to F. There is also a point positioned along the anti-meridian on the right side of the diagram. The cyan diagonal line runs from the lower left area of the diagram and terminates at point K the Kaaba, forming an angle CK approximately equal to 28.27. Note that this angle is determined within the Cartesian coordinate system. The distance from the Kaaba's position to the anti-meridian line yields to different values on its right and left sides. The distance to the right towards the anti-meridian is calculated as 140.17 for units, while the distance from the Kaaba to the left also towards the anti-meridian is 219.826 units. The comparison between these two distances results in a ratio that closely approximates the Fibonacci ratio of 5 to 8 plus 0.013 delta, indicating a significant proportional relationship between the Kaaba's location and the anti-meridian line within the context of the geometric diagram. The proportional distance from the Kaaba to the north and south poles exhibits a ratio closely approximating a comparison found within the Fibonacci sequence. Comparing these two distances 111.4 to 3 units, 68.577 units yields a proportional ratio of approximately equal to 1.6 to 5. This ratio remarkably matches the Fibonacci ratio of 13 to 8 gamma, which precisely equals 1.6 to 5, representing the comparison of two consecutive numbers in the Fibonacci sequence. It is important to note, however, that the value of the delta ratio in latitude is not equal to the value of the gamma ratio in longitude, as they are derived from two distinct ratio calculations. We use delta and gamma to differentiate the ratio in latitude and the ratio in longitude, so 8 delta does not equal 8 gamma. If the pattern of how a Fibonacci spiral is drawn is applied using the ratios in the diagram, moving from a lower to a higher value, Then the resulting directional movement aligns with the counterclockwise direction of Tawaf. Maqam Ibrahim into the Cartesian coordinate system. If we overlay the diagram's calculated position of the Kaaba onto a Google Maps view of Maqam Ibrahim, then the relative position of Maqam Ibrahim point M with respect to the Hajar Aswad point H is analogous to the position of the Kaaba point K with respect to the coordinate center point C in the diagram. The full analogy holds true if the Kaaba wall, where the door is located, is imagined as the prime meridian line and Hajar Aswad imagined as the coordinate center. This analogy is defined by the equality of the two angles. Angle MXY is equal to angle CK. Maqam Ibrahim is at 21.4262 degrees north and 39.82633 degrees east 7 GHX CRFG to GP. Analyzing the position of the Haram boundary. Haram border relatives to the Kaaba. The image shows the boundaries of the Grand Mosque with the Kaaba at its center. Various points, circles, and lines indicate different locations and boundaries, with numerical and alphabetical markings highlighting the boundary points in various cardinal directions. As follows: K equals Kaaba in the center, S equals Masjid Sayyida Isaiah in the northern point 7 GHXFRA to JC, R equals Al Rasiyadiyya in the eastern point 7 GHXFWPR plus for JW, A equals Al Akisiyya in the southern point, G equals near the main gate in the western point 7 GHX9J to PW for V, H equals Al Hudaybiyah in the western point 7 GHXCJJW7W. Red circle, south-north boundary ratio 2:1. This boundary connects the northern and southern points relative to the Kaaba, establishing the base proportionality unit, alpha. Points, point A south, Al-Akisiyya and point S north, Masjid Sayyida Isaiah. Ratio, AK to SK is to alpha to 1 alpha. Blue circle, west, south boundary ratio 3:2. This circle places the western and southern points relative to the Kaaba, all based on the unit alpha. Points, point H west, Al-Hudaybiyah and point A south, Al-Akisiyya. Ratio, HK to AK is 3 alpha to 2 alpha. Combined circle, red and blue. Since the red and blue circles share a line segment of equal length, specifically to alpha, their ratios can be combined into 3:2:1. Green circle, west-east boundary ratio 3:2. This boundary uses a slightly longer distance unit, beta, to define the western and eastern points relative to the Kaaba. The factor beta is slightly longer than alpha beta greater than alpha. Points, point G west, near main gate and point R east, Al Rasiyadiyya. Ratio, GK to RK is 3 beta to 2 beta. Note, the finding suggests that the proportional ratios comparing the lengths of line segments extending from the Kaaba to certain surrounding boundary points align with the first four numbers of the Fibonacci sequence 1, 1, 2, 3, Haram border into the Cartesian coordinate system. If we overlay the diagram's calculated position of the Kaaba onto the boundaries of the Grand Mosque Al-Haram image with the condition, the line of prime meridian passes through Masjid Sayyida Isaiah point S. The diagonal line of Kaaba CK passes through the Kaaba point K. The diagonal line of Kaaba CK and North Pole line intersect at Al Rasiyadiyya point R or point Y. Then the resulting relative position shows that Al Hudaybiyah point H is at the same latitude as the Kaaba point K, and the position near the main gate is at the same longitude as the anti-meridian 180 degrees west.